Neat. All right, I'm just gonna give you guys a quick overview of this stuff. I know it's dear God, it's gonna be a little hard to get the head around, so I'm just gonna give a quick overview and then nothing too intense. So here's an example from one of the exoskeletons that I saw, and normally without using like a middleware or some kind of overarching software scheme to control everything, you have to have like all of these things talking to each other in this kind of random assortment that's a little bit difficult to organize. So for this case, they have that exoskeleton that you can see there, and they have all these things like the data that they're getting, torques, stuff from their EMG sensors, and then of course they also have like their things that are actually calculating the physics and the logic behind it. And you can see that all of these stuff is pointing to each other in this kind of complex mess. So it's pretty difficult to do. And ideally you have a way to compartmentalize all of that. And the way that you do that is with something that's called a middleware. And so the middleware that is most common and used in industry is ROS, standing for Robotic Operating System. You can see here that the ideal case is everything points to ROS, and ROS will just shoot something right back out. And that way everything's more organized. The advantages of doing something like this is that you can modularize everything. So everything's in like a little compartment. And that allows you to, for several things, and it's ideal for this project because mostly it allows for easier expansion. When I say expansion, I mean like if we want to add something on later on in the project, let's say like we add new sensors, or like maybe sometime in the future we incorporate some kind of like vision analysis so that maybe we make the robot slightly, like the exoskeleton slightly smarter. We can do that quite easily instead of having to like rework the entire system and like hardwire that. We can just change the software a little bit, and that would require some much less work on the hardware side. So that's the advantage of using something like ROS. With the only disadvantage, of course, being that it might be slightly more difficult to implement, but everybody says that it's worth the main papers that I've read on it say that it's worth the time investment to get this working. So just one more time, a lot of people get confused on this. It's a middleware, so it's not a programming language. If you were to, when you use ROS, you program in either C++ or Python. It uses those as a backend, but it itself is not a language. It's just like a tool that you can use to help organize everything, essentially. It also comes with a bunch of nice features, but here's pretty much the basic idea of how it works. So nodes are things that are executables. So for example, if you wanted to calculate what your next step is going to be, and like specifically the X direction, that would be done at a node. And then that node would publish to a topic where other nodes are subscribers to. So if you subscribe to that topic, you get that information. And a lot of other nodes would perhaps need that. For example, the node that runs the motor would need to subscribe to the topic where the node that's publishing the next step data, so that they know where to go. So that's like the overall idea behind it. This topic node concept is the overarching scheme. It's a little bit difficult to understand without like kind of the visualization. So this is really how it works. Before I continue, is anybody confused on like the node and like the publish and topic thing going on?
I have kind of a question on that. So like how many nodes are you currently dealing with?
So let me think. Currently, we have, I believe, 5 nodes. Yep, 5 nodes that are doing things, although we haven't fully implemented obviously, like, we don't have the hardware set up, so we don't have all the, like, we're going to have a lot more nodes once we get down to it. But right now, we pretty much just have nodes for like the simulation. And so that would be things like, for example, there's a node that publishes the next movement, and then there's a node that subscribes to that and tells the simulation what to do. And so that's currently what we're working with, and it will expand once we have more sensors and more motors to work with.
So how many are publishers and how many are subscribers?
Theoretically, infinitely. You could have like as many as you wanted, but of course, like some things, like something that's publishing the sensor data, that probably won't subscribe to anything because it doesn't need to. Its only job is to take the sensor data, transfer it into something that's readable by the machine, and then publish it. So that's pretty much all it's going to do. But there's some nodes that need to both publish and subscribe. Something like I said before that, for example, would calculate the next step. That needs to subscribe because it needs to get the sensor data, and it also needs to publish because it needs to tell the motors what to do. So some are going to be both, and some are going to be just one.
Okay, that makes more sense. Thank you.
Yeah. Yeah. All right. If there's nothing else, I'll just move along here. So the main important features of ROS is hardware abstraction. So like I was talking about before, that just essentially means that you can turn the hardware, like the sensors, and get that into an electric signal that can then be used by the machines. Low device control for those kinds of motors and getting them to turn and getting outputs to the exact amount that you would like. The most important one being the message passing between the processes. So it's what allows for everything to talk to each other. And lastly is code reusability. It is an open source software, which is the best part about it. If other people have done something that you are doing, you can take that code and modify it slightly and make it work for your own needs. Currently, it has a ton of usage with like robotic arms. So there's a lot of data on that right now. Not a ton on exoskeletons, although a lot of companies are starting to use it. So a lot of research papers that are coming out are pretty recent. So there's not a whole ton of code reusability necessarily for that just yet, but there will be in the near future. And this is very much so like an up and coming thing, especially with the advancement that they just made. It used to be ROS and now it's ROS 2, and it works on more platforms. It's more stable. So it's definitely kind of got the leading edge right now, which is a very nice thing to work with. So this is one of the essential parts of ROS that allows you to visualize whatever you're working with, in our case, an exoskeleton in the digital realm. It's called the URDF. So in order to set up a URDF, you pretty much you set up these things like parents and childs and joints, and they all kind of interconnect in this massive tree-like structure. And to give you an example of that, kind of here's what we're working with, and it looks very complex, and you don't need to worry about any of the details here. Just if you take a look at like the top one, it says link 2, and so that corresponds to this like shaft right here, and then the subsequent joint after that is joint 2, and that corresponds to this knee joint, and then we have link 3, which corresponds, and so on and so forth. Like link joint 3 would be the ankle joint, link 4 would be the foot. So it all just kind of cascades into this tree-like structure where you can add things like the mass value, the inertial tensors, add different geometries. In our case, we got kind of complex geometries because SolidWorks can export directly to this, which is really nice. So you can get some like really complex simulations in here. Like you can see, we created the torso and the feet, and those are just blocks. But creating something like those legs is significantly more complex, but it's made a lot easier because you can just export your SolidWorks model and take that and use it. So that really helps with kind of visualizing it online. And again, the advantage of that is that you can create simulations, make sure that your model is correct. And it also just, anytime you can visualize your code, it helps make things a lot more sense and maybe see like where things are going wrong a little bit easier. So this is just another really useful part of ROS, and it can do that natively, but it also has kind of this adjacent thing called Gazebo. And Gazebo is not ROS, they're different, but they're often used in tangent with each other. And so Gazebo is specifically for simulations. So you can take that URDF that you created using ROS, and then you can simulate it in Gazebo, and you can add more physical effects to it. And you can like see how something would respond if you increase the weight on it or something like that. And so the hope with this is to be able to have a simulation where you can more easily test your exoskeleton without having to fully like manufacture and produce a prototype and then see what happens and then realize that it's not going to work for whatever reason. And so that's really the use of Gazebo, and it is a project that we are working on. It's not the main project. Really, we're focusing on kind of that ROS messenger stuff I was talking about before, but this is just kind of like the other half of it that you guys probably heard about in presentations that we're working on. So it's definitely something that's a useful tool and something to keep in mind. But that's the end of that bit. And then finally, I just want to go briefly over some inverse kinematics. I'm not going to take you guys to the math of it because it's kind of exhausting and a little too complex. But the whole point of this, right, is that at the end of the day, we want to be able to say, hey, this is the next position that we want to go to. What kind of torques and what kind of outputs do we need from the motors to get there? So this is like really where all of that comes into play. And so when you do forward kinematics, that's the easy stuff. That's like you have a force in the joint space and you want to figure out what your position will be in the Cartesian space. And so we've all done that when we've taken like dynamics classes and stuff like that. That's not particularly difficult. Inverse kinematics is when you have a position and you want to figure out the forces that it will take to get you to that position. That's significantly more difficult because there could be infinite solutions, or there could be just one in any range in between. So you almost have to have a smarter setup, a smarter computer setup in order to get that done. And that's the thing that Laura was working on for her senior project the entire time. And it's something that we're still trying to get through. There are a couple like sub modules that are developed to help you with that, but at the end of the day, a lot of people say that you really kind of have to create, if you're doing something novel and you're building your own robot from scratch, not like something that somebody else has done, then you generally have to make your own inverse kinematics. And so that's the real tricky part to what we're trying to work on right now, and is something that's essential to ROS and also to the robot as a whole. So and again, I'm not going to walk through the math too much, but it really is just comes down to a bunch of complex matrix math and using the Jacobian, which is like the first derivative of whatever you're working with. So you use that, and then you try to figure out the smoothest path to the position that you're trying to get to. And that's pretty much the overall of kind of what we're working on the software side right now. Any questions on it?
I have a couple of questions. So with your code, you said you're getting a lot of your code from research papers. Is it mostly research papers on exoskeletons, or do you kind of take stuff from like robotic arm research? Or
Yeah, a little bit of both for sure. So a lot of the code that we have right now is actually definitely written by ourselves. We've just taken the outline that they use and then integrated it with our own robot. Um, and so it's more, sorry, when I say like taking code, we're more just like taking their outline and then filling in the parts that work best for us. And so that is usually exoskeleton stuff. Although originally when we first started doing this, it was just arm stuff because that's all we could find. And recently there's been more and more exo stuff, but it's still not a lot. So a lot of what we work with is like arms and then try to transfer that into the leg kinematics.
Okay, cool. And then with the inverse kinematics, like since you're finding a position or you have a position and you're trying to find force, do you use like do you use like multiple positions that a user might be in and then kind of take a graph of that or something, or how does that work?
Yeah, so one of the main methods is called the Taylor method, and so you have you like you said, you and the computer doesn't do this, but like for our visualization purposes, you would like put the point that you're at on a graph and the point that you want to get to on a graph, and you pretty much draw a bunch of lines, and then find lines that are tangent to that, and that's where the Jacobian that I was talking about comes in. And in order to find the smoothest path from the position that you're in to the position that you're trying to get to. And so, like I said, it's not what the computer actually does, but for us to understand it, that's how we would do it.
Okay, that makes sense. And then with the Gazebo versus ROS, so you're saying Gazebo, you're using it more for simulation,
Yeah.
and
No, sorry, continue.
sorry, no, I'm trying to like think through my thoughts. Okay, and then ROS, you're like inputting code into it, or kind of what, could you outline the differences a little bit more between
Yeah,
the two?
for sure. So again, like I was talking about before, ROS isn't a coding language, it's a middleware. So it's a tool that you use that has a lot of functionality. And so, for example, like you would, that is a lot, that's where we're writing most of our code because we're like creating things like those nodes, or we're creating those URDFs to visualize the robot. And that's all done within the framework of ROS. And like I said, we code currently in C++ a little bit, but they also have a Python option. That's also partially what we're doing. And so that's where like everything, like all the magic happens that I was talking about before. Like when you create those like pretty much highways for messages to go through, you're doing that using ROS's tools. Whereas Gazebo, you're not really coding or doing anything with really code in Gazebo. Actually, Gazebo is just a way to simulate the URDF that you already have. And so that's just a matter of like figuring out what your inertial tensors are and like what your weights are. And so that's more of a like concrete and mathematical tool, whereas ROS is definitely more of like a coding software tool.
Okay, that makes sense. So are you inputting like the code, like you get all of those different inputs and then ROS kind of organizes them and like makes those highways, and then you input that code that ROS gives you into Gazebo?
Yeah, pretty much. Like whatever ROS is giving you, Gazebo is then taking and simulating and like making it a reality pretty much. ROS has a tool for that, but it's a lot more like low end. You don't really get like physical results. Gazebo's whole point is that it's supposed to give you like physics in response. Like if I do this, what's going to be the force output? And Gazebo should be able to simulate that for you pretty much. Yeah, so it's like exactly like you said before. It's taking everything that ROS is giving it as the inputs, and then it's figuring out what the output would be.
Yeah, that makes a lot more sense. Thank you.
Yeah. Cool. Well, and that's all I had on the simulation and kind of what ROS and Gazebo is.
Yeah, thank you. I had like a couple more questions.
Go for it.
So with the SolidWorks models that you're inputting into Gazebo, how complicated are those? Like, do you just basically right now have kind of what we were talking about earlier, like some cylinders, and or like how do you like the current SolidWorks model? Like, would you want to build another
Yeah.
one?
So that picture on the right there is Gazebo. And when we were talking about like getting those smoother cylinders, that was more for the sake of figuring out some of our physical parameters, like the inertial tensors, because you can imagine like the difficulty of finding the inertia of something like that, where it's got like a million different little like divots and points, and like it's a very difficult shape to work with. So in order to simulate, we really just need an approximation, and that's where those cylinders come into play. And so we can put that into a different software. The one that we were looking at is called Mesh Lab, and it creates kind of this. It gives you what the inertia of your thing would be, but like I said, it can't be too complicated, and that's where that comes into play. But Gazebo can be as complicated as you would like.
Okay, so you're able to add inertia into Gazebo.
Yeah, we're able to add inertia into the URDF. That's what you see there on the left. If you like look beneath link 2, you can see that there's like an inertial tag with inertia in it. And so like I said, a URDF is something that's within ROS. It's a framework that it gives you. You have to follow those exact steps to create a link, and you can add inertia. And so that's where inertia is added, and then that's just like an added thing for Gazebo. If you want to get physical results, like the force that your step is going to make, then you do have to have inertia in your URDF.
Okay, cool. I had another question. If you go back to, I think it was your first slide with all the complicated pathways, the one before that, what currently, like out of all these things slash like all the additional things you're working on, like what are those blocks that you're trying to input into ROS? Not to get too deep into it, but
sorry, so when are you referring to like the EEG data, for example? Like how would that go into ROS? Is that what you're asking?
yeah, exactly. Like what are you, there's like the IMUs, the NMS.
Yeah.
What are you currently working on?
Yeah, so like I said, the main thing that ROS allows us to do really is to connect everything into one continuous system that's receiving and taking data, not a bunch of like individual parts that are hardwired together. So the goal of this is pretty much everything would circle back to like this Raspberry Pi or this Arduino or something, and that would be able to output, that would be able to send the data to ROS. And so the ideal case scenario is that each of these individuals are throwing data together. And when you get this data, it's usually not like usable. It's in some like electrical form, or it's difficult to analyze. And so what ROS can do is put that into a readable format and then send that data to something like to what I was talking about before, a node, which would then use that data to calculate like your next step, and then it would shoot out that information and that result to a motor, which would then perform that. And then the infinite loop recycles, right? The data from the sensors come back, and then the node will calculate its next position, and the motor will then make that into reality. And so it just like keeps looping like that pretty much. And like I said, the advantage is that if you want to like add a sensor, or you want to try to like add some new functionality, it's a lot easier to do because everything is already combined into this system. And so all you have to do is just like plug it into the system, and you can start adding things.
That's awesome. Yeah, that makes a lot more sense. Thank you.
Yeah.
I have a quick question. So for like your simulations, is the input a torque or a speed? So like you kept talking about forces, and so is the input a torque?
Oh, yeah. Exactly. So, well, it's a little bit more because we can't, well, I guess we could, but as of right now, we don't actually like give it torques or anything like that. Like right now, we have a very basic setup where we can give it pretty much like, it comes out in the form of a sine wave. And so we input this sine wave, and these joints move in accordance with that sine wave. And they turn to be like whatever degree you are on that sine wave pretty much. So right now we're not actually giving it torque, we're giving it information about what degree to turn to. And it doesn't give us torque or anything like that. That would most likely be an output that we would get from the simulation. Although I have seen it before where you could like input this much torque and see what happens. But again, we need to have like a more complete simulation, like more weights, more inertia, that kind of stuff.
Yeah.
All of our pieces don't have that yet, so it can't, like Gazebo can't do it.
Yeah, so basically you're inputting position values for the angle or like the joints.
Yeah.
Okay.
Yeah, right now it's very crude and not something that you could do in real life. But
yeah, I mean, like I was just thinking about like for our inputs, if you have a motor, you're going to give, if the motor has an encoder or something, you can give it a position value, and then it'll go to that position.
Yeah.
Figure out how to get there. And then, but also you might not have an encoder, then you just give it a voltage, and maybe you have a sensor that gives the feedback. But I was just thinking about how much of the practical application is going into the simulation, or is it just position values for right now?
Yeah, so for right now, there's not a ton of what would actually be practiced in real life, like you were talking about. Ideally, we get to that point. Like I said, the simulation currently is more of a side project because we need ROS. We need to like build the actual infrastructure a bit more robustly right now for it to actually do those outputs like you were talking about. So it's pretty stationary right now with where it's at with just the sine wave that I was referring to before. But yeah, ideally we get to that point, and that should happen.
Yeah, that sounds good. All right, cool.
I just kind of had a logistical question. So obviously it's been hard to get people for ROS. Like what would an ideal amount of people, or like if you had joining members, like they would have to initially learn the software?
Yeah, that's definitely been the toughest challenge. I know that every team has had like drop off, but I think software has had a very large drop off, mostly because I think the learning curve for this has been a little much for some people. And so that's where I'm hoping that like I like your idea with the YouTube video. I think that'll help a lot with directing people more on how to go. and to help increase kind of that retainment off the bat. But yeah, the ideal, I mean, we have a lot of different projects that we have to get done. And so it's not necessarily the number of people, it's the people with the right skill sets. And if we don't get those skill sets, then we need a lot of people to make up for that. So it's hard for me to like estimate right now. But we should have a lot of different sub projects that require different specializations. So, I mean, I suppose ideally we have a team of like at least 7 or 6, but yeah, 7 or 6 should be able to split it up pretty equally.
Okay, cool. And is Gazebo as hard to learn? Like, let's say I joined your software team, which I'm sorry, but I'm not gonna do that. But let's say you're like, oh, here's the code, Christy, like input it into Gazebo. Is that super complicated to learn?
No, I would say not. I think that the difficulty with that is that it's very mathematical in nature. Like it's figuring out things like I said, like you have to figure out inertia, you have to figure out like that kinematics that I was referring to before. And I think that's the major stumbling block for a lot of people is it's just a lot of math.
Would a math major be good?
It's a good point. They maybe I should look into a math major. I don't know. I'll have to think about that, honestly. I don't know why it hasn't crossed my mind before, but that could be interesting. Yeah. I mean, I know Laura was saying that her #1 struggle was not even like the implementation of what she was trying to do with inverse kinematics. It was the difficulty of like figuring out the actual math behind it. So maybe I'll take a look at that. Cool. Well, thanks for the questions, guys.
Oh, thanks for a good presentation. Yeah, awesome. Oh, hey, Ashwin.
Hey, what's up, guys?
A couple of random little logistical things. Paul, is your girlfriend still making the logo?
Oh,